All right, we are going to look at what we call the unit circle to help us figure out how all this trig stuff that we've been working on is going to fit together. Okay, we're going to go through the unit circle and we're going to label degrees first, starting with our 45s. So at our starting point here, we have 0 degrees. If we keep going, this would be my 45 mark. Okay. This would be 90 degrees. Okay, so I want you to keep going with that 45 mark in each quadrant. So this one would be, we're adding 45 degrees each time, right? 135. Okay, add another 45 and we get 180. Add another 45. 180 plus 45. 225. Okay. Adding another 45 gets us 270. And another 45. 315. Okay. And if we go all the way back to where we started, we are at 360. I'm going to rewrite this here. Okay. Now we're going to go through with 30 degrees. Okay. This much is 1/6 of the top half, right? So that's our 30 degree mark. So now we're going to go through and we're going to count in 30 degrees. So we've got 30, then 60, then we would land at 90, right? Then 120, okay, 180, 210, 240, 270 we've already marked. Another 30 would be 300, and last one 330. And then we're back to our 360. Okay. So we've got all the degrees marked in there. Now we're going to go around with radians. Okay. That's your other blanks. So at the starting point, we are at 0 radians. Once we get all the way back, we're at what? 2 pi. So this can be referred to as 0 or 2 pi radians. How much is 30 degrees in radians? It's 1/6 of pi. All right. So just like before when we counted in 30 degrees, now we're going to go and count in sixths. Okay? So we have pi over 6. 60 degrees would be 2/6 or pi over 3. 90 degrees would be 3/6 or pi over 2. Okay, let's keep going. 4/6 would be, okay, 5/6 and 6/6 or 1 pi. Okay, going down 30 degrees, again adding pi over 6, we end up with 7 pi over 6, and then what? 8/6 would be 4/3. Okay. 9/6 is 3 pi over 2. Okay. 10/6 5 pi over 3. All right. And then 11/6. Okay, so what are we missing? We're missing the 45 degree ones, right? What's 45 degrees in radians? Pi over 4? Okay. So 45 degrees we're going to label as pi over 4. The next would be 2/4 or a half. We already have that labeled. Our next blank would be 3/4. Then we get to 4/4, which is pi. Then we have 5/4 and 6/4 we've already labeled as 3/2 and 7/4. Okay, so if I gave you this blank circle, could you go around and do that much? Degrees and radians? Okay. Next year in pre-calc, You are going to be able to do all of this, including the coordinates that we're going to label now. You are going to basically want to have it memorized before you take your first trig test. Okay? I'm going to show you some patterns. They're going to show them to you again next year, but there's some tricks to helping you create this circle. Okay? We talked the last couple days, we've defined our trig functions in terms of x, y, and r. Okay? How did we define cosine? All right, x over r you said? And then sine was y over r. We had circles with different radius, yes? So we divided by whatever the radius was. Well, in a unit circle, what we mean by a unit circle is that the radius is 1 unit. So what's going to happen if you take all these x coordinates and divide by 1? Nothing happens, right? I mean, it stays the same value. And if we take all our y coordinates and divide by 1, there's still whatever the y was. So in a unit circle, we basically can just think of x being our cosine and y being our sine. So all of these coordinates around the outside are going to have the cosine value as the x coordinate and the sine value as the y coordinate. Okay? So let's label our quadrantal angle ones. Okay, those are the easy ones. If I'm at 0 degrees or 0 radians, what's my coordinate over here? 1, 0. Okay, if I go up to 90 degrees, I'm at coordinates 0, 1. If I'm over here at 180, negative 1, 0, and down at 270, 0, negative 1. Those are the easy ones, right? That won't be hard next year to plug in. Before we get to our next coordinates, if I'm at 30 degrees here, would my x value be bigger or smaller than 1? Think about starting at the origin here, right? If I go over here to get to this point, have I gone all the way out here to 1? No, I haven't gone that far. Yes? I've had to go up a distance, so my y value is bigger than 0, but my x value is still inside that 1 mark. Would that be true for all of these? Yes? So the maximum x value I'm going to have, the minimum x value I'm going to have is negative 1. The maximum would be a positive 1. Does that make sense? All of those points on my circle are going to be in between those values. Would that be the same case for y's? Yes? All right. So what we're really saying there is that the cosine of whatever your angle is will always be a number between negative 1 and positive 1. And the sine of an angle is always going to be between negative 1 and positive 1. So if you get an answer and you say the sine of theta is 2.7, I'm going to say it can't be, because sine's always between negative 1 and positive 1. Okay? All right. Filling in our 30, 60, 90 ones, or sorry, 30, 45, 60 ones. You're going to have to think back to our triangles that we drew. Okay? So if you need to flip in your notes back to your special triangles, I need to know the cosine of 30. What's the cosine of 30 degrees? Look that up. Or visualize it. Do we have it? Cosine of 30? Root 3 over 2? Okay, so cosine is going to be my x value. I'm going to have a root 3 over 2 there for 30 degrees. What's the sine of 30? Same triangle. What's the sine of 30? 1/2? Okay. What if we switch to 60 degrees? What happens to my sines and cosines? They what? They switch, right? Because my opposite and adjacent sides switched. So for 60 degrees, my cosine would be 1/2, My sine would be root 3 over 2. Okay? Cosine's x, sine's y. How about for 45 degrees? That's the triangle where both legs are 1 and the hypotenuse is root 2. So sine and cosine of 45 are both what? Yep, rationalized would be root 2 over 2. Okay, now we used reference angles yesterday to help us find trig functions outside of that first quadrant. Remember doing that? So let's picture I'm over here at 150 degrees or 5 pi over 6. What's my reference angle? 30 degrees or pi over 6? Okay, so we said that the sine and cosine of 150 degrees is basically sine and cosine of 30 degrees, with the exception that we might have to change it to a negative. Yes? So if I go from this point here, 30 degrees, and I go over here and flip to 150 degrees, my coordinates are the same except for which one? The first one, right? The x turns to negative. But it's at the same distance this way and the same distance up that I was on the other side in quadrant 1. Does that make sense? So those coordinates are going to come over to this side, but my x is going to be negative. Okay, now looking at 45 degree ones. Compare that and 135. They're the same height, right? So my y coordinates are going to be the same. My x's are just going to be opposites. So I'm going to bring root 2 over 2 over to this side, but my x is going to be negative. Would the same thing happen for 60? Okay, so I'm going to have negative 1/2 and root 3 over 2. If we go to quadrant 3, what signs do I have for my x and y coordinates? Both negative? Okay, so think about this. If I'm up here at 150 degrees and I go down to 210, what's going to change? They're both 30 degrees from the x-axis. The only thing that changes is instead of y being positive, now y is negative. So when I take all these quadrant 2 ones and flip them down to quadrant 3, both coordinates have to be negative. So for 7 pi over 6 or 210, what are my coordinates? Anybody? Negative root 3 over 2 and negative 1/2. All right. My 45s are always the root 2 over 2s? Yes? For x and y? So negative root 2 over 2, negative root 2 over 2. And for 240 degrees or 4 pi over 3, we'd have negative 1/2 and negative root 3 over 2. Yes? Okay. Now I take those and I flip them over to quadrant 4. What do I know about my signs for x and y? Okay, so x is going to turn positive, y is still going to be negative. I'm bringing them straight over, right? So I'm going to have positive root 3 over 2, negative 1/2 for 330 degrees. For 315, I'm going to have positive root 2 over 2, negative root 2 over 2. And for 300 degrees, I'm going to have positive 1/2 and negative root 3 over 2. Okay? Now, that's a lot of stuff. When I told you you're going to have to memorize this, now you're probably thinking, oh my gosh, how am I going to remember all that? But if you know quadrant 1, all we have to do is flip them over the axis, right? And change one of our coordinates from positive to negative. And you guys know that x is negative over there, right? In quadrant 2. So the key is, can you get quadrant 1? Well, there's two ways to do it. You can draw your 30, 60, 90 triangles, your 45, 45, 90 triangles, right? And look up your sines and cosines. Or there is a pattern. Look at all of the focus on the 30, 45, 60 part. all the denominators are 2. Okay, so that's set. All of my fractions have a denominator of 2. All of the numerators are technically square roots. Because what's the square root of 1? 1, right? So we've got 1s, we've got root 2s, we've got root 3s. And there's a pattern. We start with a 1 here, right? Sine of 30, 2, 3. Then we've got 1, 2, 3. Just goes in order. 1, 2, 3 up, 1, 2, 3 down. So technically, all you need to know is one of them. And that's why earlier in this unit I said, I memorized the sine of 30 is 1/2. I get that one locked in my head, I can generate everything else from it. The 2's match top and bottom, they match x and y, right? So I already know the 45s. They're the easy, root 2 over 2's for everything. It's the root 3 over 2's and the halves that you have to keep straight. If I know this is a 1 here, I know it's going to have to be paired with the other number, root 3. Okay? So lots of little patterns inside it that make it easier than it looks at first glance. Okay. On the next couple of pages, I've just given you a picture of this so you can refer back to it without flipping your page each time. We've talked about some of these things. It says a circle with a radius of 1 unit is that unit circle. For every angle, there is a point where the terminal side intersects the circle. The coordinates of those we said were cosine for x and sine for y. We talked a few minutes ago about this part. Okay? Sines and cosines are going to vary between -1 and +1. That's your min and max. This says the domain of theta is everything. Think about it. Could we keep spinning around that unit circle over and over and over and over again? Yes. So my angle can be anything. I can spin in a positive direction and go into infinity. I can spin in a negative direction and go to infinity. Would you agree that going from 0 to 2 pi completes one full rotation? Okay. Now, we're going to start graphing these today. There are graphs for all 6 trig functions. We are only going to focus on sine and cosine this year. You'll get the other ones next year. Okay. I can show them to you if you're curious. But for sines and cosines, the way we are going to label our axes, this is going to be theta. Okay? Our horizontal axis is going to be our angle. So we're going to mark things like pi over 2, pi. Okay? We're going to have radian measurements on that. For the y-axis, that's the coordinate. So if we are graphing cosine, we are going to be looking at our x values all the way around. If I'm graphing sine, I'm going to be looking at my y values. Okay? We said sine and cosine have a maximum of 1 and a minimum of -1. So a basic sine graph that we haven't changed at all is going to bounce between -1 and +1. Okay? What happens to my numbers? We'll start at 0 here, and let's look at sine values. Okay? So 1/2, root 2 over 2, root 3 over 2, all the way up to 1, and we started with 0. So if I'm going from 0 to 1, as I go around that circle, what's happening to my y-coordinate? Is it getting bigger or smaller? It's getting bigger, right? All right, keep that in mind as we do our first graph. So for the basic sine and cosine functions, we refer to it as the period or the cycle. All right, usually they use the term period. One period is once around the unit circle. Okay, so for sine and cosine, the period is 2 pi. That's not the case for all of them, but for sine and cosine. So for everything we're going to do this year, I want you to think of the period being 2 pi. To graph a sine or cosine curve, it says to divide the period into 4 equal increments. So what I always do, we take our normal period of 2 pi, we want to cut it into 4 pieces. Well, what's 2 pi divided by 4? 1/2 pi, right? So my increments are going to go by half pi's. Okay? I need 4 of them. For one complete cycle, I have to get out to 2 pi. So on our horizontal axis over here somewhere, write 2 pi. We want to cut it into 4 things. So we're going to cut it in half. We're going to cut it in half again. And we said each increment should be a half a pi. So this first one is going to be pi over 2. Then we have pi. What's my next one? Halfway between 1 pi and 2 pi. 3 half pi's, right? 1.5 pi. Okay. So do I have 4 equal increments? I sure do. Do I have increments that are going up by pi over 2's? Okay. So we marked the increments on our graph. The next key thing is you have to know where to start. Sine and cosine start at different spots. So go back to our unit circle here. If we look at 0 degrees or 0 radians, my cosine value is 1, my sine value is 0. Yes? So at 0 radians, which is where we're going to start, right? This would be 0 radians at the origin. At 0 radians, sine should be 0 and cosine should be 1. Okay. Now I'm not going to keep scrolling the board up here, but you've got your unit circle on your paper. What is the sine? We're graphing sine first. What is the sine or the y coordinate at pi over 2? Up at 90 degrees. What's my y coordinate? 1. So at pi over 2, I'm going to be up at 1. Where's my sine value at pi? I'm back to 0. How about at 3 pi over 2? Think down at 270 degrees. Okay. And when I get back to 2 pi, I am back to where I started, right? At 0. Now we're not going to take time to plot every single coordinate on that unit circle. I'm not going to put in all the halves and root 3 over 2's and all of that. But if I think of, if this is pi over 2, right, split it, this would be pi over 6, my first tick mark, right, 2, 6, 3, 6. I could plot all those points. At 1/6, I'm up at a half, right? At 2, 6, I'm at root 3 over 2. So I could plot all those points. We just don't bother. We know what the general shape should be, and we draw it in. Most common mistake is students want to play connect the dots. These are not straight line things. If I had plotted the 1/2, the root 2 over 2's, the root 3 over 2's, I would be getting a curve piece. Okay? So what a sine curve looks like: a hill and a valley. That is one period of a sine curve. Now, technically, we could keep going. All right? But if it says graph 1 full period, that's what I want to see. 1 period. No more, no less. So we marked our axes. We figured out where we have to start, and we put our 5 key points. So where do we hit 0? Where do we hit the high points? Where do we hit the low points? All right, let's do a cosine graph. Similar. Period is still 2 pi, so I'm going to split my horizontal axis into 4 chunks, going from 0 to 2 pi, and label them. We're going by halves Again, I'm going to mark my vertical axis with 1 and -1 for my high and low. And where does cosine start? At 0 radians, what is your cosine value? Cosine's x. What's the x-coordinate at 0 radians? What's the x-coordinate? Right? My coordinates at 0 radians is 1, 0. X is 1. So cosine's going to start at 1. Start at 1. Up at pi over 2, what's my cosine value? 0. At pi, what's my cosine value? -1. At 3 pi over 2, what's my cosine? Back to 0. And at 2 pi? Back to 1. Whoops, sorry. Putting it in the wrong spot. Okay, so similar, it's got curves to it, but this one's going to look like this. So more like a bowl or a vase kind of shape. Okay, so the key thing is you do not want to be playing connect the dots. You don't want these straight in here, right? There is a curve to it. We are assuming you know that, and because of that, we don't make you plot all of these points in here. Okay, but it's got to look curved. It gets easier as you do a whole bunch of them. So I've got about 50 for you this weekend. I'm kidding. All right, we're going to look at 2 transformations of our curves. Are we doing okay with, do we get the basic one? And do we understand how we're getting those points from the unit circle? Okay. So the 2 things that we're going to look at is we're going to change it vertically. So we've done all kinds of transformations this year, right? If I alter it this way, we're talking vertical stretches, compressions, flips. Okay? So the A value is going to do all of that. It's going to stretch, compress, it's going to flip. When does it flip? If it's negative. Yep. The absolute value of A, that means it's always going to be a positive answer. Okay? The absolute value of A is called the amplitude. Okay? The amplitude is going to tell me how big the stretch or how small the compression made it. And again, if it's negative, it'll just flip over. So, first example. Determine the amplitude of y equals 2 sine x, then graph a basic y equals sine x as well as a y equals 2 sine x so that we can compare what's happening. So, very quickly, I want you to go back. We've graphed this out already. Let's get it marked on here. Sine starts where? At 0. If you want a little trick, sine starts at 0, cosine starts at 1, right? Cosine has a 0 in the word, but it doesn't start there, right? Sine has kind of a 1 in the word. It's an I, but it looks kind of like a 1. It doesn't start there, okay? They're always opposite. So we know sine starts at 0, and it goes up to 1. All right, so at pi over 2, I'm at 1. At pi, I'm at 0 again. Okay, that's the hill part. Now I need the valley. So I'm going to go down to -1 and back to 0. So hill and valley. Okay? So what is our amplitude if there's a 2 in front? Amplitude is just the positive version of that number, right? Absolute value of 2 is 2. So that means I'm going to have a vertical stretch of 2. Well, what happens when I stretch 0? It stays at 0. So all my 0 points are still going to be zeros. What happens if I stretch that 1? It now is at 2. Okay, and a negative 1 goes to negative 2. So the effect is that my graph is just stretched vertically. Okay, let's try a cosine one. Let's go ahead and graph the cosine first. Cosine starts at 1. All right, then we do down to 0, negative 1, 0, positive 1. All right, so we want our little bowl looking thing. Try to hit your dots. All right. Amplitude for this function. Remember, we want the absolute value of it. So amplitude would be 3. Okay, that means we have a vertical stretch of 3. What does the negative in front do? That negative a value? It's going to reflect over where? Okay. So what we can think of is just multiplying our y values by negative 3. Okay. Do our zeros go anywhere? No. Anytime we're doing vertical stretches, compressions, flips, zeros don't go anywhere. But our 1 is going to get stretched to become a 3, and then it's going to flip over to be at negative 3. Okay. Our negative 1 is going to stretch to become negative 3, and then it's going to flip over the x-axis to become positive 3. Our last one here, same thing. Stretch it to be 3, flip it over. We're down here at negative 3. So we have a reflected graph that's been stretched. So it looks taller and it looks upside down. Questions on what A is going to do? All right. So describe for me, what would this do? My amplitude is 1/2, so I actually have a vertical compression. Okay, so it's going to get smaller. We're going to skip over the graph of that. Let's just move on. All right, the second piece that we are going to look at uses the variable, or the letter b. Okay, this one is inside with your x. Okay, so the a in front stretches vertically. We call that the amplitude. The b term is going to affect how wide it is. And we haven't done a lot of horizontal stretches and compressions this year. You will get those more next year and as you continue on. But your first term, that a piece, changes the vertical height. B changes the horizontal one. Okay? And the one thing to keep in mind, with horizontal changes, it's always opposite of what you think. So like when we did transformations and we had things like, okay, a parabola, we've shifted it to the right 2 spaces, but we saw a -2, right? So we see a -2, but we actually go right. If we see a +2, we actually move left, right? So horizontal things are always kind of opposite of what they look like in the formula. What that means is when we see numbers like this, a 2, it's not making it get stretched out horizontally, it's actually compressing it horizontally. Okay? I'll show you why. So the B term is going to affect how big one period is. when we graph that one cycle, we went from 0 to 2 pi. Now we're going to change that spacing. Okay, so B is going to cause a horizontal stretch or compression, which means it's going to adjust the period for our graph. To find the new period, and you might want to highlight this, circle it, put a big star by it, something. Normal period for sine and cosine was 2 pi. It's going to get divided by whatever b is. Okay, so the new period will always be 2 pi over b. All right, so for example 4, we have the equation y equals sine of 2x. It says determine amplitude and period, and then graph 2 full periods. Well, what's the amplitude? Still 1, right? We haven't changed anything vertically. Period, though, is going to be 2 pi divided by b. But in this case, b is 2. And 2 pi divided by 2 is 1 pi. So instead of us going from 0 to 2 pi to fit our curve in, we're going to have to scrunch that down. And now we have to fit that whole curve between 0 and 1 pi. Okay? The increments that we are going to use, remember we always take the period and we divide it into how many equal chunks. So my increments are going to be pi divided into 4 chunks. So pi over 4s. All right, so my tick marks, 1, 2, 3, 4. I need 4 equal chunks. To get to that 4th chunk, I should be at pi by then, right? If I go by pi over 4s, does that work? Now, I'm writing them down at the bottom just because with this thick marker, it kind of hides the dots that I'm going to be putting in there. Okay, but you can certainly label them up by the axis. Okay, so we are graphing sine. We haven't stretched it vertically at all, so we are bouncing from 1 to -1. Okay, up and down. At 0 radians, at my starting point, what is my sine value? Sine starts at 0. All right, so I start at 0, and then where do I go? Up to, go all the way up to pi over, go up to pi over 2. Same 5 points that we had before. So we started at 0, we go up to 1, then we go back to 0, then we go down to -1, then we go back to 0. Yes? Because think about it, if I put this angle of pi over 4 into my equation, what's going to happen to it? It's going to get multiplied by 2, and it's going to turn into pi over 2, and the sine at pi over 2 is at 1, right? So you should be having those same 5 points. All we're doing is changing the spacing horizontally a little bit. Does that make sense? Okay, so here's my curve. Now it's said to graph 2 full periods. You can graph the second one to the right of what you've got. You could graph it over on the negative side. Doesn't matter. All right? One period took us pi spaces. So 1, 2, 3, 4. I'd end here at 2 pi. And I would have my second period going and doing the same thing it did before. Same shape. I'm just repeating it. Okay? So I have 2 cycles. All right, let's try another one. Shifting to cosine this time. Amplitude. All right, still 1. Period. We have to take 2 pi and divide it by 4, which means the period is really going to be pi over 2s. Okay, so we start out having from 0 to 2 pi to fit our curve in. Then on the last example, we scrunched it down from 0 to pi. Now we're scrunching it down even further. We're saying from 0 to pi over 2, we have to fit that whole curve in. Okay? Don't make it so small that you can't figure it out. You can label your tick marks, make them as big as you want, as long as you've labeled them. So if we know that the period is going to be pi over 2, how big will our increments be? Pi over, divide it by 4, right? Pi over 8's now, right? 1/4 of pi over 2 is pi over 8. I don't want to make tick marks like this, okay? There's no way I can picture my graph in that spacing. So just label it. My first space is going to be pi over 8. My next one would be 2/8, which would be pi over 4. Then I have 3/8, so 3 pi over 8. And then I have 4/8, which is pi over 2. And that's what our period was supposed to be, correct? All right. They do want 2 full periods. Where's my last one going to end? At 1 pi? You don't have to label all those tick marks as long as you've shown me the pattern. Okay. We are graphing a cosine. Cosine starts at 1. So we're going to put our dots in. Okay. We start at 1. Then we go to 0. Then we go down to -1. Back to 0. And up to +1. There's my first cycle. Okay. Again, I've scrunched it down. Second cycle, same thing. High, back to 0, low, back to 0, high. Okay? In order to get credit for these trig graphs, you have to have your tick marks labeled. All right? Otherwise, there's no way for me to tell if you've done it correctly, because I can have the same picture for 10 different questions. It's all in the spacing. Okay? All right. We aren't going to graph these. I just want you to look at D here. What is the amplitude? Amplitude this time is 2. The period, though, the period is 2 pi divided by what? Dividing by 1/2 is the same as multiplying by 2. So what's happening to this one? It's getting bigger, right? The number looks small, but our graph is getting stretched out horizontally. So now, for my tick marks, if I'm going 4 pi for a whole period, each tick mark is going to be pi. All right, now I'm going to stretch this out for a second so that you can actually see that it is stretched some. It's a cosine graph, right? Cosine amplitude is 2, so instead of starting at 1, we're going to start at 2. Then we go down to 0, right, at pi. Then we go down to -2, back to 0, and up to +2. So again, high, 0, low, 0, high. And I can write a second period over here, or either side, doesn't matter. Okay? So you guys are going to do the trig stuff. What is that, 4 day 1? Trig 4 day 1? I'm going to get you some graph paper.